welcome. This is the next Excel FP1 video. Now, in the last video, I looked at simultaneous equations using the matrix equation, okay, in terms of what we essentially did in that video as we looked at another way of solving simultaneous equations, obviously for x and y, but using a slightly different method, okay, where we literally just put one, so the, as I can't, actually, no, I'm not gonna, I was gonna try and give a summary, but I'll probably just end up confusing you. Anyway, so we'll try not to do that. Okay, so in this video, what we're going to be looking at is, transformations, okay? Now, there are many types of transformations that you can, that we can do with matrices, okay? We can rotate them, we can enlarge them, or we can... the other thing, I mentioned something else as well, I'll probably just forgot it, okay? So, but anyway, the shorthand is, what we're going to be looking at in this video is we're going to be looking at rotations, okay? Now, I'm going to combine a series of rotations, okay? So the first few that I'm going to talk about is obviously the 90 degree, the right angle one, and then we're going to look at the full 180 degree, then we're going to look at 270 degrees, and then I'll show you a way of working out any degree they ask for, okay? But obviously the first few, there's a slightly different, easier way of working them out, but then we work out just theta when they don't give us, when it's not 90, 180 or 270, okay, becomes a little bit more difficult, but as I said, nothing too more. Now, the thing that you need to be able to understand to work through this video is something called unit base vectors. Now, hopefully, as I said, you should know what a vector is. But if you don't, what essentially a vector is it's just a direction. It's a magnitude and direction, okay? So a vector could be that, with the magnitude of 3 coming in the x direction. But just to give you a bit of an overview, okay? As I said, I do proper videos on vectors a bit later on, okay? But what we do is we have essentially what you would normally. I'm just going to draw a quick sketch here. So take a second. Okay. So, imagine this is your normal x direction, that's your normal y direction, then we've got a line, an arrow coming out the page. When we talk about a unit base vector, okay, we talk about one vector, so a magnitude of 1 in each direction, but we don't call it a magnitude of 1 in the x direction, no. We call that unit base vector, we call that I. Okay, so 1 in the x direction is called I, okay, because it's a unit base vector. 1 in the y direction, we call that, well, it's the next letter in the alphabet, j. So we call that j as a unit base vector, j. That's 1 in the y direction, okay? But then we have this other direction we call z. Okay? And we call this unit base vector 1 in the z, so out of the page we call that the vector k, the unit base vector k, okay? So that's what all of that means. Alright, and just in essence we call it, if we were to write in column vector form, okay, so this is sort of getting into C4 territory now, we put the I at the top, so the I direction, so if it's positive or negative, obviously in the x direction, and then we put the j, okay, so is it positive or negative, is it towards the top of the y axis or is it below, okay, and then finally we put the k direction, okay, so that's essentially what we're looking at. However, for this, for FP1, you only need to be able to understand, for these transformations really, the first two. Okay, so the I and J. If you don't get what I mean by this Z direction and the K unit base vector, that's completely fine, because that's something we look at in C4 if you go on to do maths in your second year. Okay, so as I said, that was really a brief overview into what unit-based vectors are, but you do need to be able to understand definitely the I and J, what I mean by that. But you probably won't be given it in I and J form, okay, but as I said, you just need to be able to understand what we mean by that. But as I said, hopefully it isn't too difficult, but if you do want a bit more practice on it, please do check out my C4 tutorial on vectors if it's up here. If it isn't, I'm sure there'll be another vectors video somewhere on my channel. Okay, so as I said, there is a key. What I'm going to draw here actually is just a quick sketch really of y and y and x. Okay, and obviously I'm not going to label it fully in terms of x coordinate 1, x coordinate 2, etc. I'm just going to draw a quick triangle. And then on the right hand side, what I'm going to draw is the unit base vectors. Okay. Now we need to, because we're in, as I said, this is a 2D. That's why we're not considering the k, because the k directional vector, the k direction is out of the page. We're not going to consider that. Okay. So we only need to consider the I and j. So obviously there's coordinates going in the x direction and there's coordinates going in the y direction. Okay, so when we rotate this, now we're going to be looking at the anti-clockwise, by the way, in this video. So you may get it clockwise, but you could just quite clearly reverse what we do. Okay, right, so 90 degrees in anti-clockwise sense. Well, obviously we're going to be moving it that way. So when we shift this triangle 90 degrees, okay, so we turn it 90 degrees, it's going to end up looking something like this. Okay, so hopefully that makes some kind of sense. But we need to, if we had the coordinates of these vertices, okay, because when you're looking at redrawing this, you're not bothered about the individual points, because obviously there's straight lines. So you just need to work out the transformation of each vertice, okay, or each end point of the shape, okay, and each end point of the shape has an x and a y coordinate, okay. What I mean by that is, well, obviously you know what I mean by that, but what I'm trying to say is it has a I and j component that is moved, okay. So what we need to do is consider the I and j, okay. So what I'm going to draw is two little sort of diagrams, okay. Okay, so what they are, what I've drawn is just basically a set of axes. I've not labelled x and y on them, but you can do, okay. Sorry guys. And we're just going to label our I and j direction vectors. So remember, that's in the x direction and the y direction, okay. The first one I'm going to do is the I, okay. So that's going to be, in that form it's 1, 0, which means 1 in the I direction and none in the j direction. And when we rotate that 90 degrees, okay, we're shifting this horizontal line, okay, and when we move it 90 degrees, obviously that creates a right angle. So that's what we're doing here. So now it becomes none in the x direction and 1 in the y direction. In other words, it's 0, 1. Okay, it's a unit base vector. Okay, so it moves vertically. But when we consider the j directional vector, which is already vertical, okay, that is starts at 0, 1, and then when we shift that 90 degrees to the anti-clockwise, we get minus 1, 0. Okay, because we've moved it, we've shifted it to the left, okay, so we've rotated it 90 degrees anti-clockwise. Now, because as I said, each one of these, each vertex has an I and a j component. We need to apply this shift, because a unit base vector says, if it had a magnitude of 1 and we shifted it, this is what would happen. But obviously, each one of these points, when I say magnitude of 1, what I mean by is it's not an x coordinate 1. A magnitude of 1, an x coordinate 1 would have, mean that the x coordinate would be 1, okay? So for every x coordinate, okay, we call that in the I sense, okay, that moves 0, 1, okay? It rotates anti-clockwise by 90 degrees 0 to 0, 1, okay? And that's if it was at 1, 0, okay? So obviously it isn't, but the magnitude of the shift stays the same, but we just sort of apply it to, because essentially it's a ratio kind of thing. So this is what it's moved by, and we need to move each point by the same amount. But that's just considering the I direction. We also need to consider the j direction. That rotation, because obviously there's a straight line here, which indicates obviously a j or a y sort of component to this. Okay, so what we need to do is basically there's this same formula, okay, for each. What we need to do is come up. Sorry, before that, we need to come up with a transformation matrix. And what we mean by this is something we times all the individual vertices of the shape by, so that they all move by the same amount. Okay, because obviously they're all going to move by the same amount in terms of they're all going to rotate by 90 degrees. And the transformation matrix, the first half, the first column in the transformation matrix is determined by the shift in the I components, okay? So because we've gone from 1, 0 to 0, 1, that's the shift. So the ending shift is the end coordinate, 0, 1. So that's the first half of the transformation matrix. And the second half of the transformation matrix, in terms of the second column, is made up by the shift of the j components, okay, from 0, 1 to minus 1, 0. Okay, so the second half of the transformation matrix is minus 1, 0. And the same principle, obviously, we're going to have a different transformation matrix when we shift the 180 degrees and 270, but the principle stays the same. If the first column is the first shift, okay, in the I direction, what's happened to the unit base vector of I, and what's happened to the unit base vector of j is in the second column of the transformation matrix, okay? So I'm just going to label that Tm, but you know Tm represents the transformation matrix. Now, there is a common theme that runs through. Actually, it even goes on to when we're talking about the when we were just rotating it by a degree that that is not a nice degree, so it's not 90, 180, or 270. There's the same principle that stays the same. Obviously, the transformation matrix is slightly different, but as I say, the method stays the same. Okay, obviously we're going to be rotating it through different amounts. And for the degree, we're going to be using a slightly different method of those. That is just going on from basic trigonometry. We're going to go to that in a minute. But as I said, the basic method, okay, so if we label these points A, B, C and D, okay, so the individual nodes, you can think of it like that. What we do, okay, so I'll write out the standard formula. Okay, so the coordinates of the new shape is equal, okay, because obviously you might be able to draw that, is equal to the transformation matrix, Tm, times the original point. So if it's A, you would put A coordinate first, so you times it by the coordinates of A, the coordinates of B and the coordinates of C. A, B and C representing this original matrix, okay? So A, B, C. Hopefully that makes some kind of sense. If you can understand that, you can apply that method to every rotation that you come across. And I think it even applies to the enlargements and stuff. Basically, it's the original shape is equal to the transformation matrix times the points of the shape. Okay, that applies to the rotation, slightly modified, I think, when we look at enlargements. But the principle of the end product is equal to transformation times whatever you might face, okay? And that is obviously your equation. But as I said, for rotation, that is the same principle. It says new shape coordinates is equal to transformation matrix times the old coordinates, because the transformation matrix is basically the magnitude by which it's changed. And the magnitude by which it changes is shown by the shift. Okay, so hopefully that makes some kind of sense. So as I said, that applies for all angles that you will come across. However, as I said, the only thing that will change is the transformation matrix according to whatever shift you're doing. But that shift will always be the same for a 90-degree rotation. Okay, anti-clockwise. Obviously, it will change. You can work it out going the other way for clockwise by 90 degrees. Okay, obviously, instead of going anti-clockwise, obviously you would go the other way, and it would produce a slightly different transformation matrix for each one. But as I said, you could just apply the same theorem and to different questions. But as I said, if that doesn't make sense, please do drop me a comment on the video and I'll try and get back to you. Okay, so that's 90 degrees. That's fairly simple. So you might want to take that down, because what I'm going to do now is discuss the 180 degree shift. Okay, so what I'm going to do at the side is just write down the transformation matrix for 90 degrees, because we've just worked out as 0, 1, minus 1, 0. So, okay, I'll come up with this little table. Transformation matrix, 90 degrees, and I'll put 180 degrees, 270 degrees, and theta degrees. Okay, so that's a little table that you might want to come across, okay? Because as I said, this principle stays the same for each rotation through a certain number of degrees. Okay? But obviously we're going to be looking at a different transformation matrix. Okay, so all I'm going to rub out is this transformation matrix and the actual shift. These two little diagrams. Okay, but the principle I'll draw them back on. Okay. So, what we're going to look at now is we've done 90, so we're going to do 180. So you do the same principle, except obviously we end up in the bottom third quadrant. Okay? So obviously that gives us sort of this kind of triangle. So the shape doesn't really matter, because you'll end up working it out in the end. Okay? So we end up with this right angle triangle that we've shifted through 180 degrees. And obviously you can prove that yourself through doing just cutting out a bit of card, basic year 1 stuff. Okay, right. So we're going to apply the same formula, but we need to now come up with the transformation matrix. We're still going to rely on our knowledge of unit-base vectors, okay? Remember we were saying unit-base vectors, just a vector in the magnitude of x or y with the magnitude of 1. Sorry, just had to do a few things. Okay, so now we are looking at rotating the shape by 180 degrees. Okay, so as I said, the same principle applies of the coordinates of the new shape is equal to the transformation matrix times the points, the vertices of the original shape. But now we need to obviously work out the transformation matrix for 180 degrees. So just like we worked it out for 90 degrees by looking at the movements of the I and J unit-base vectors, we're going to do that again. But obviously we're going to be rotating them unit-base vectors by 180 degrees. Okay, so what I'm going to do is exactly what I did before. Draw the little diagrams, okay? Right, and the one on the left is obviously going to be the I unit-base vector, okay, which has a unit-base vector of 1, 0. Okay, 1 in the I direction and 0 in the J, or 1 in the X and 0 in the Y. Because we're rotating it 180 degrees, we're going to be shifting this all the way back to front, okay? So instead of 1, 0, it's now going to be minus 1, 0. Okay, so that's the first part of the transformation matrix, okay? So it's minus 1, 0. Now, the next little diagram we're going to be doing is we're looking at the J components, okay? Which has a unit-base vector of 0, 1. Okay, when we rotate that by 180 degrees, we turn it back to front. Okay, which means we therefore have 0, minus 1. And that's the second half of our transformation matrix, 0, minus 1. So our transformation matrix for 180 degrees is, is it minus 1? It should be, shouldn't it? Sorry, let me double check. Yep, it's minus 1, 0 and 0, minus 1 because remember the first part of the column vector is the I, so is it left or right? And it's not, 0. And the J, is it up or down? Okay, and it's down, so it's minus 1 because it's a unit base vector. Okay, so that's a transformation matrix of 180 degrees, which is minus 1, 0, 0, minus 1. Okay, so what we're going to look at now is, obviously that would be the case, so you could apply that like we did for the 90 degree rotation. Alright, and that is very similar actually to reflection in the X and Y axis. Well, this is, they're all linked, the transformations, but it's just a bit of a heads up, okay? So do check that out, video later on. Okay, so what we're obviously going to be looking at now is we're going to be looking at 270 degrees. So if you continued that rotation, but instead of just rotating it 180, you would rotate it 270, it'd obviously be in the bottom right quadrant. And quite clearly, it'll look like this. Triangle there. And just like we did with 90, 180, we're going to be rotating the I and J unit base vectors to come up with the transformation matrix for 270 degrees. Okay, so we're going to draw our little graphs again. Okay. Alright, so on the left diagram, we'll be doing our normal I unit base vector, which is 1, 0. Okay, and when we rotate that by 270 degrees, okay, it ends up being 0, minus 1. Okay, because obviously it's now, I was going to say there, but you get what that is. So that's the first half of our transformation matrix, 0, minus 1. To have the second half, or the second column of our transformation matrix, we need to rotate the J column vector. And the J column vector, remember, is 1, 0. Okay, I'm going to rotate that by 270 degrees. Obviously we get it in over here. And that therefore becomes, oh sorry, the j vector isn't 1, 0, sorry, it's 0, 1. Yeah, and that becomes therefore 1, 0, I do apologise. So that's the second half of our transformation matrix, 1, 0. Okay, so the transformation matrix for 270 degrees is 0 minus 1, 1, 0. Okay? 0 minus 1, 1, 0. Okay, and that's for 270 degrees. So they all seem fairly self-explanatory so far. You can quite clearly see how all of them are quite relatable. But what we're going to go on now is we're going to look at the rotations, okay, if we were to not rotate it by such a nice angle. And the reason they're nice angles is because obviously they end up in the first half, the second half, or middle, as I said. Yeah, they lie on something specifically. It's not an angle halfway here because otherwise it'd be quite difficult to try and work it out. And that quite difficult bit is what we're going to be working out. Okay, so, but really, it's as hard. I know it sounds a bit, stereotypical, but it's as hard as you make it to be. Okay, and obviously it's still going to be quite difficult. But just using basic trigonometry. Okay, so what I'm going to draw is our diagrams that we've been drawing so far, and approach it from vaguely the same perspective. But I'm going to be looking at it like when I was showing these. I rotated all of these anti-clockwise. Okay, so this is all these. Just to clarify, all them transformation matrices are for anti-clockwise clockwise rotations. Okay, now you can obviously just do the opposite of that for clockwise. Probably should have mentioned that before, but hopefully you saw that. And because all them are anti-clockwise, I'm going to be doing the angle theta anti-clockwise as well. As I said, they could ask you clockwise, which would just be the opposite of these in terms of it be, I don't know, you just work it out, it'd be 0 minus 1, 1, 0 for 90, for 180 it'd be 1, 0, 1, 0, 1, and for 270 degrees it'd be 0, 1, minus 1, 0. Okay, so as I said, that's anti-clockwise. We're going to be continuing that theme now. So just drawing our I and J's. I is 1, 0, and J is 0, 1. Okay, and if we rotate it anti-clockwise, and I'm only going to keep it in the quadrant it's in. Okay, so I'm going to rotate the I, so it looks like that. Okay, so we get this, and we're rotating it through theta there. And in the J, okay, I'm going to rotate it in the first quadrant it enters. Okay, so top left. And we've got a little theta there. Now what I'm going to do, because obviously there's no way of us working that out at the moment, so I'm going to turn it into a right angle triangle. So obviously we're not considering this whole distance, the curvature, we're just considering this angle. So there's nothing that says we can't just turn that into a right angle triangle. So we're going to. Okay. So just find a different colour pen, choose a different colour pen, sorry. Okay, so I'm just going to cut these off into right angle triangles. Okay, so obviously you can see the right angle there. Now if I call, because obviously we've rotated them both through the same angle, okay, so the hypotenuse, if we call the hypotenuse 1, okay, because when we do cos of something we assume the hypotenuse to be 1, okay, so if we both assume the hypotenuse of both these triangles to be 1, we also, because we've rotated it through the same degree, the height we're going to call of each triangle, we're going to call that B. Okay, when I say the height, it's the that bit. Okay, so it's directly from the floor. When I say from the floor, the x-axis right up to the hypotenuse, and from here it's essentially from the y-axis to the hypotenuse. But basically, it's the red line. Okay, that's labelled B. Okay. Right. Now what I'm going to label next is the base of the triangle. Okay. So it's the distance along the axis, and I'm going to call that A. Okay. So the green arrow represents little a, and the red arrow represents little b. Okay. So just like before, when we were working out the transformation matrix, we would work out the first column would be made by the end value, so to speak, of the rotation of the I, and the second column would be the end answer of the rotation of the J. Okay, we're going to use that principle because there's nothing that's changed. Okay, we're still rotating it through an angle, but it's just not a nice one. Okay, so what we want here is we want to get to, okay, well, what is this point? Okay, so that point there, the point at the top of the triangle here. Okay, so hopefully you can see that there. We want to get to that point. I'll try to colour in. Okay, and if you just look at that in the coordinate sense, well, it's quite clearly A units across and B units high for the J, for the I component, sorry, so it's A, B. But for the J component, where it's shifted, well, it's moved left by B unit, so it's minus B, okay, and it's moved up A, okay, so it's minus BA. So therefore it's AB minus BA. That's the transformation matrix. But we can't put AB minus BA. We need to know what AB actually represents, okay? Well, we can, using basic trigonometry. Okay, so it's obviously the use of sine, cosine and tan. But we're not going to be using tan, really, because it's a little bit more complicated. Well, it isn't, but it's just easy to use sine and cos, because I can. Badoosh. Okay, so anyway, assuming this was just a normal right angle triangle and you weren't dealing with transformations of matrices, let's just imagine how you would work out, okay? Because what we're trying to work out is this angle. Now, you would obviously use the common GCSE idea of SOHCAHTOA, okay? And we want to use sine or cosine because we want to use B and A, okay? And, well, obviously, sorry, we can't use B and A. The reason we're using sine or cosine, sorry, should have probably mentioned this, rather than just give you a kind of crude explanation to it and accept it. If we use tan, then we would be using two unknowns in our answer. So basically, if we were to use tan, we would change A to, like, I don't know, something B tan theta. And what was the point of that? You're just replacing one unknown with now two unknowns. That's just pointless. Okay, so that's why we use sine or cos. But as I said, hopefully that kind of, it doesn't really matter. Okay, so as I said, we're going to use sine or cos. Now, for A, well, if you want to work out A, we've got the adjacent, okay, to both of them, and we've got the hypotenuse, okay? So the only one that has adjacent hypotenuse is cos, okay? So cos, SOHCAHTOA is adjacent over hypotenuse. So cos theta is adjacent, which is A, over hypotenuse, which is 1. And if we times both sides of this equation by 1, okay, we get A to be equal to cos theta. So that's our change, that's what we're going to input for A, okay? Now, you might have been expecting me at that point to do, well, we want to know what theta is, so theta is the cos inverse of A. Well, we don't know what A is, that's what we're trying to find out. So we can't rearrange this cos theta equals A over 1, so we can get theta, because we would be told theta, okay? We wouldn't be told A. Okay, and that's what we're trying to work out. As I said, this transformation matrix. So do the same kind of principle for B. And because we're using the opposite in the hypotenuse, we would use sine. Okay, so sine theta, if you sine SOHCAHTOA, so so is an opposite over the hypotenuse. Okay, so sine theta is the opposite over the hypotenuse, B over 1. So the same principle applies. B equals sine theta. And you just apply B equals sine theta and A equals cos theta into your transformation matrix. Okay, so if we write the official transformation matrix over here, A is cos theta, so it's cos theta. Okay, and column 1, row 2 would be sine theta. This is the transformation matrix. And then column 2, row 1, okay, would be minus B or minus sine theta. And column 2, row 2, the transformation matrix, would be A, which is cos theta. So in other words, the transformation matrix is cos theta, sine theta, minus sine theta, cos theta. Okay, so that's that there. Okay, as I said, you would apply the exact same principle working out any rotation. Okay, and I think I'll go into how you can apply it for reflections and enlargements as well. Well, I think you can. Anyway, I've shouldn't have said anything at all because I had a quick look and I'm pretty sure you can. I'll shut up because I'll just confuse you. Okay, so you can use that for any rotation method that you would like. Okay, as I said, that is all for anti-clockwise. So you can just apply that method and work out what the transformation matrix would be if you were rotating it clockwise, which would obviously just be opposite in terms of you turn on positives, negatives, and negative, positive. Okay, but as I said, if you wanted to go through the clockwise variation of that, you can do. But if you want me to do another video doing the clockwise transformation matrix transformation matrix of the rotations for the FP1, please do let me know and I'll put another video up there. But as I said, you don't have to remember these transformation matrices. You can just come up with them on the day of the exam. I actually even I think they might even give them in the actual formula sheet. I'll just have a look now for you. So I do apologise. FP1 formula sheet. This is the only revision video on YouTube where the person doing the revision video actually decides just to pause the video and do whatever he wants to do. I just have a quick look on the old interweb for the actual formula sheet. Okay, so do apologise. Sorry, I really do apologise. I'm just checking if them transformation matrices are on the actual formula sheet. So just loaded it up now. As I said, I wouldn't recommend trying to remember them unless they're not on the formula sheet. Don't think they are. No, they don't appear to be. Guess you just have to remember them. Doesn't really matter, to be honest. No. Okay, so sorry about that. As I said, there's nothing too much. Just you have to remember them transformation matrices. You can just come up with them on the day of the exam. There's not that much to remember, really. Okay, but as I said, you can note them down and just learn to remember them. So nothing too difficult, really. As I said, it would just be a quick sketch at the side of your exam. Alright, so thanks for watching, and hopefully it's been of some use to you, and we'll see you in the next video.